Ever think about how much cool stuff happens when you shrink things way down?
Like what?
Well, imagine like sculpting with light itself.
Yeah.
Bending and shaping laser beams super precisely in these teeny tiny systems.
Okay, yeah. I can see that being important.
Right. It sounds kind of sci-fi, but it's actually like essential for all sorts of things.
Yeah.
Like we're hearing more and more about these super precise laser surgeries and even, those quantum computers everyone's talking about. But the way we usually shape light with lenses and stuff, even, the fancy tools, it often involves like tons of trial and error to get the light to behave exactly how we want.
Yeah. Traditional optics.
Right.
It's incredibly useful, but it often boils down to kind of educated guesswork.
Right.
A lot of fiddling around to get the right setup.
Mm-hmm.
And that gets really tricky when you're dealing with things smaller than the wavelength of light itself. Things get pretty complex down there.
So today, we're going to dive into something completely different, a totally different approach to this whole beam shaping thing.
Yeah.
Something that could be like a huge game changer. Imagine like fundamentally programming the shape of light.
At the smallest scale.
Yeah, at the smallest scale, not through like complex trial and error, but by like actually leveraging the very fabric of physics itself.
Interesting.
So that's what we're exploring today, this crazy new way to shape light beams at the nanoscale using topological physics.
Topological physics.
Yeah, it's wild. And our deep dive today, is focused on a paper, Topological Beaming of Light, Proof of Concept Experiment,
Okay.
by Choi and his colleagues, published just this year in Light Science and Applications.
Right.
And this paper, it talks about using these things called Jackie-Rebbe states, which I'll be honest, sounds super advanced to me,
Yeah.
within these specially designed surfaces called metasurfaces.
Mhm.
And the idea is to get like this amazing control over the profile of a light beam. It's like this way more systematic, efficient way to get the beam shapes we need without all that super complicated optimization.
Right. What's interesting here is that, like, fundamental shift,
Mhm.
instead of relying only on the physical shape or the material properties to kind of bend the light,
Right.
they're tapping into these, like, underlying principles of topology.
Right.
And the Jackie-Rebbe states, like you mentioned, they offer this really unique way to, like, trap and control light
Yeah.
at these
In a
interfaces.
very like robust way.
Yeah, yeah.
So the potential here is really exciting. Like the possibility of creating almost any custom shaped beam, even a flat top beam.
A flat top beam.
Yeah.
That's a big deal for a lot of applications.
Can you break down why that's so important?
Sure. So a flat top beam, it gives you this even distribution of light intensity over a certain area.
Mm-hmm.
And that's super useful for things like, manufacturing materials,
Hmm.
even looking at biological samples under a microscope, where you need that consistent illumination. You don't want any, like, hot spots or anything.
Right, right. So let's dig a little deeper into why beam shaping has been such a challenge, especially at these like tiny nanophotonic scales. Okay.
What makes it so difficult with traditional optical elements?
Well, the thing is, when you shrink everything down to the nanoscale, the wavelengths of light become like comparable in size to the optical components themselves.
Oh, I see.
So it's really hard to use those traditional lenses or gratings
Well-
in the same way we do with, larger optics.
Makes sense.
To get a specific, like, tailored beam shape, you often need these super intricate patterns
Oh, wow.
and extremely fine control over these teeny tiny structures.
Mhm.
Like we mentioned before, this means you need complex design processes,
Right.
lots of computational optimization.
It's a lot of simulations.
Yeah. And running simulations, tweaking designs. It's like until you get exactly what you want,
Right.
and that can take forever. And it's not always easy.
It's like, trying to paint a miniature masterpiece with, like, a giant brush.
Yeah, exactly. So how does this field of topological photonics offer this different approach? And what exactly are these Jackie-Rebbe solitons that keep popping up in this paper?
Well, topological photonics, it offers a whole new way of thinking about manipulating light. Instead of focusing on the, like, exact geometric shape, it looks at these fundamental topological properties of these photonic structures. Think of it as like a property that's, like, inherent to the shape or structure.
Yeah.
Something fundamental that can't easily be changed.
Mm.
Like how a donut always has one hole.
Yeah. Yeah.
So these topological properties, they're super robust.
Okay.
They don't really get messed up by small imperfections in the manufacturing or, like, changes in the environment. Now, those Jackie-Rebbe solitons, those are a specific type of localized wave
Right.
that could exist right at the boundary between two regions that have different topological properties.
Interesting.
Like, imagine two materials side by side, but they have different topological characteristics. That's where you might find these solitons.
Okay.
And these were actually first predicted in particle physics as solutions to a fundamental equation, the Dirac equation.
Dirac equation. Huh. Sounds intense.
Yeah, it's pretty fundamental. But the interesting thing is, researchers have found out that you can design certain photonic systems that behave mathematically very similarly to electrons, as described by this Dirac equation.
So you're saying there's a connection between, like, the physics of particles and how light behaves in these systems.
Exactly. And that's the key to this whole topological photonics thing. They've essentially found a way to translate a fundamental property of particles, something akin to their mass, into a tool for shaping light, with far greater precision and predictability than we could before.
So instead of trying to find just the right pattern to bend or scatter the light, you're creating this kind of special zone where light gets stuck because of these topological properties.
That's a great way to visualize it, yeah.
Yeah.
The topological properties dictate the existence and behavior of these localized states, those JR solitons, giving you a more direct way to shape the beam. No more extensive trial and error.
The paper mentions this GMR analogy quite a bit.
Right.
What's a GMR structure?
So GMR stands for guided mode resonance. They're basically thin films with these tiny repeating patterns. Kind of like, think of it as extremely fine gratings.
Okay.
And these structures can trap and enhance specific wavelengths of light through a phenomenon called resonance. Now, the really cool insight here is that the strength of this resonance, specifically how strongly the light is reflected back and forth within this GMR structure, what they call the Bragg reflection rate,
Okay.
can actually be mathematically linked to the mass of a Dirac fermion.
Hold on. So you're saying a property of light bouncing around in this tiny grating is acting like the mass of a fundamental particle.
That's the analogy, and it's a powerful one.
That's pretty mind-bending.
It is. But think of it this way. That Bragg reflection, it causes the light waves to, like, bounce back and forth within the structure. And the rate of this bouncing, this kappa they talk about, it plays the same role mathematically as mass does in that Dirac equation. This lets them connect the behavior of light in their GMR system to the physics of things called topological insulators.
Topological insulators, huh?
Yeah. These are materials that have some really interesting properties. And these properties, they're related to the Dirac equation.
All right. So I think I'm starting to get it. So this mass or Bragg reflection rate, I can have different signs, right?
Exactly.
And that's where those topological phases come in.
Yeah, just like a Dirac fermion can have a positive or negative mass,
Right.
the GMR structure can be designed to be in one of two topologically distinct states or phases.
Okay.
So you have the topologically trivial phase, where kappa is positive,
Mhm.
and then you have the topologically non-trivial phase, where kappa is negative.
I see. And those phases are characterized by some other fancy properties.
Yeah, they're characterized by things called topological invariants. These are like fundamental characteristics of the system that are protected. They don't change easily, even with imperfections. And that makes the light shaping more robust. And importantly, these two phases can't smoothly transition into each other. Something significant has to happen, like a gap in the energy spectrum closing at the critical point where kappa equals 0.
Okay. So what happens when you, like, bring these two different topological phases together?
That's where it gets really interesting.
Yeah.
When you create a junction, a boundary, between a region with a positive mass, positive Bragg reflection rate, and a region with a negative mass, something special emerges.
Happens.
A localized state appears right at the interface. This localized GMR state is the photonic version of the Jackie-Rebbe soliton. And the key point here is that the shape of this localized state, how the light intensity is distributed, what they call Fx, is directly related to how you've designed the distribution of this Dirac mass, that kappa or mx, across the surface. They even give a specific equation showing this relationship. Kappa x is proportional to the derivative of fx divided by fx.
So by carefully designing how that Bragg reflection rate changes, you can directly influence the shape of that light beam that gets trapped.
Precisely. It's like having a much more direct and systematic way to get that beam profile you want.
I see. So the next part of the paper gets into the experimental stuff, like how they actually created these GMR structures in the lab and how they tested all these ideas.
So how do they make them?
Well, they used these advanced nanofabrication techniques, including something called electron beam lithography, which basically lets them create these incredibly fine patterns. They started with a thin film of silicon nitride on a quartz wafer and etched these precise patterns into it. Crucially, They designed different areas of the sample with different fill factors. Think of it like the ratio of the width of those strikes in the grating to the total width of a repeating unit.
Right.
This fill factor is a key way they can control the Bragg reflection rate, and therefore the effective Dirac mass.
Okay, so they made the structures,
Yeah.
but how did they actually analyze the spectral properties,
Yeah.
of something that tiny?
They use something called angle-resolved spectrum analysis.
Okay.
They basically shone a beam of light onto the sample at different angles and then measured the spectrum of the light that passed through. This lets them map out how the light interacts with the structure at different wavelengths and angles.
So they could see how the light was behaving and how it was affected by the topological property.
Exactly. And this revealed some key things, like the energy bands of their photonic crystal, and it allowed them to actually observe that topological phase transition as they changed that fill factor.
The paper mentions a spectral flip
Yeah.
and a bound state in the continuum, or BIC.
Right.
What are those?
So the spectral flip, that refers to how the resonant frequencies of the structure, they shift as you change that fill factor. It's like a clear sign that the topological properties are changing. The bound state in the continuum, that's a particular type of resonance
Okay.
that theoretically should, trap light perfectly and not let it escape.
Really?
Yeah. It's pretty cool. And its position within the spectrum also changes in a specific way as you go through that topological transition. Think of these as clear fingerprints. They tell the researchers that they've successfully created these distinct topological environments for light.
I see. And what about those junction structures, where they brought those two topologically different regions together? What did they see?
Right. At the junction, they observed a very clear resonance within the band gap. And that band gap, that's a range of frequencies where light normally can't propagate through the structure. But this resonance, showing up around 1.3 micrometers in wavelength, that's the experimental proof.
Of the Jackie Rebbe state.
Exactly. And its spectral characteristics, like the specific wavelength and the sharpness of the resonance, it matched their computer simulations really well.
Cool. So they saw the spectral signature.
Right.
But did they confirm that this JR state was actually confined in space, not just in the frequency spectrum?
They did. They performed something called local spectral analysis.
Okay.
Imagine a tiny magnifying glass looking at only a very small part of the sample at a time. They used this small measurement opening, 50 micrometers wide, and they scanned it across that topological junction. And at each position, they measured the transmission spectrum. Yeah. And they found that the JR state resonance was only strong and clear when their magnifying glass was positioned very close to the junction interface.
So it really was confined to that specific region.
Yeah, unlike other resonances, which were present across the entire uniform region.
So they had their proof
It did.
that the light in this JR state was localized in space.
Yeah.
The paper mentions that the measured width of this localized state was a little bit broader than what their theoretical calculations predicted. Any idea why?
They think it's mostly because their measurement aperture wasn't infinitely small. A 50 micrometer opening, it introduces a bit of averaging, kind of like a slight blurring, which can smear out the finer details of the JR state's spatial profile.
Okay, that makes sense. So they saw the spectral signature, they saw the spatial confinement,
Right.
but the really exciting part is the beam shaping.
Yeah, achieving that flat top beam.
So how did they actually go about designing and testing a structure to do that?
Okay. To get that flat top beam, they designed a more intricate junction structure. Instead of just two regions with different topological masses, this one had three. One with a positive mass, a central region with approximately zero mass, this critical phase, and then another with a negative mass. By choosing the width of that central zero mass region very carefully, they could create a JR state that had that flat top spatial profile.
Clever. And they did those local spectral analyses again on these more complex structures.
They did.
Okay.
Same local resonance spectrum analysis, but on these new junction designs. And they observed JR state resonances at the wavelengths they expected. And the spatial profiles of the reflected light at that resonant wavelength, inferred from their local measurements,
Right.
showed those promising flat top shapes.
Right.
Which got wider as they made that central region wider, just like they predicted.
But how did they actually visualize the light beam itself? Like the light leaking out of the structure?
Yeah.
How did they confirm that flat top shape?
Well, because their GMR structures are passive.
Meaning they don't actively generate light?
Right, they don't generate their own light. So they had to use this kind of clever technique to infer the shape of the emitted light. They basically shone a broad, even beam of light onto the sample,
Okay.
and then collected the light that was reflected back. Then they compared the reflected beam from that specifically patterned topological junction area
Mm-hmm.
to the reflection from a nearby area on the sample that didn't have any pattern.
Oh, I see.
So by subtracting the reflection from the unpatterned area, they could isolate the light that was actually being shaped by that topological junction.
That's a really neat way to do it. So what did they see?
They measured the intensity of this, like inferred leakage radiation at different distances away from the surface of the sample. And for the junction structure, with the specific width of that central critical region, 127.5 micrometers, they observed a beam profile that was much broader than you'd expect from just a simple reflection of the initial beam. More importantly, the intensity profile across the center of the beam, it was much more uniform, showing a clear flattening that looked a lot like a flat-top beam. This was super different from the typical Gaussian shape you'd see reflected from a uniform GMR structure without any topological junction.
So they really did it. They got a flat top-like beam just by using this topological design.
They did, but the paper does mention some limitations to this first demonstration.
What were those?
They acknowledge that the experimental flat-top beam, it wasn't like a perfect rectangle of light.
Right.
They believe this is mainly because the efficiency with which the guided light within the structure radiates outwards, what they call the first-order diffraction amplitude, it wasn't perfectly uniform across that whole junction region.
Oh, I see. So ideally, the shape of the emitted light should perfectly match the spatial profile of that JR state.
Exactly. But if the strength of that outward radiation varies across the junction, it can distort the shape of the emitted beam.
Got it. Why wasn't that first-order diffraction amplitude uniform?
Well, it has to do with how they designed their unit cell, the smallest repeating element of that grading pattern. For their single-ridge unit cell, the main way they have to control that Bragg reflection rate, kappa, which is what lets them create the mass distribution, is by changing the fill factor, the width of the ridge compared to the gap.
Mm.
But the problem is, changing that fill factor also affects how efficiently light radiates out of the structure. That first-order diffraction amplitude, which they call epsilon 1, as well as another parameter, epsilon 2.
Okay, so it's like a balancing act.
Yeah, it's a balancing act. And with this simple design, they found that you can't really adjust epsilon 2, which influences kappa, without also affecting epsilon 1. It's like trying to adjust the volume on a stereo, but you accidentally also change the bass and treble at the same time.
Right. To get that perfectly shaped beam, you need to be able to control that mass distribution kappa of x while keeping the leakage efficiency related to epsilon 1 of x constant. And with this single ridge unit cell, those two things are linked.
Exactly. But they do have a proposed solution.
What's that?
They suggest moving to more sophisticated unit cells that have multiple features within each repeating unit. By having, say, multiple ridges with adjustable widths and positions, within each unit cell, they get more flexibility in the design.
Okay.
This could let them independently control that second-order parameter, epsilon 2, and therefore the mass distribution, kappa, without messing with the first-order diffraction amplitude, epsilon 1.
So more control, more precision.
Exactly. They even suggest that things like the thicknesses of the layers in the structure could be used as additional knobs to really fine-tune the properties.
Interesting. So this isn't just some abstract theoretical thing. There are real-world applications here.
Oh, yeah.
What kind of things can we actually do with this?
The authors of the paper, they highlight the potential for improving surface-emitting lasers,
Okay.
which are lasers that emit light directly from their surface. Imagine being able to control the shape and direction of the light coming out of a laser like that without needing any extra lenses or optical elements. It could lead to much more efficient and versatile laser sources for a bunch of applications.
That's amazing. Any other potential uses?
Yeah. They also mentioned other possibilities, like shaping light that's guided in topological channels on a chip, and even improving how efficiently light can be coupled into and out of resonant structures.
So we've gone from this theoretical idea of using topological properties to control light to actually shaping laser beams in the lab.
Yeah.
And there are already potential applications in things like lasers and integrated photonics.
It's a really nice example of how fundamental physics concepts, ideas that were originally developed to understand those tiny particles and, exotic materials are now being used in cutting-edge nanophotonic design.
Yeah, and the fact that they got that flat top beam,
Yeah.
even with the current limitations,
Yeah.
that's a really strong indication that this new approach has huge potential.
Yeah.
It's exciting.
It is exciting. And while there are still, those hurdles to overcome,
Mm.
particularly with getting those perfectly shaped beams,
Yeah.
due to that uniformity of the light emission,
Right, right.
the idea of using these more complex multi-part unit cell designs, it seems really promising.
It does. It offers a way to achieve even greater precision and design flexibility in the future.
So we've covered a lot of ground today. We started by looking at those challenges of shaping light at the nanoscale,
Yeah.
using traditional optics.
Right.
Then we dove into this new method based on topological photonics, specifically using those Jackie-Rebbe states in these carefully engineered metasurfaces.
Yeah.
And by creating those topological junctions and carefully controlling the photonic equivalent of the Dirac mass,
Mm.
the researchers have shown that it's possible to get that customized beam shaping, even, showing a promising flat top beam.
It really makes you think about what else is possible. If we can control something as fundamental as light at such a small scale, what other amazing technologies could this lead to?
It's a big question. If we can gain this kind of precise control over light at the nanoscale, how could it revolutionize not just lasers and quantum computing,
Right.
but all sorts of other fields? Could we see, like, radical new imaging technologies?
Possibly, yeah.
Maybe new incredibly sensitive sensors,
Yeah.
or even like entirely new ways of interacting with matter itself. What other crazy applications might come from this whole like marriage of topology and photonics?
It's definitely something to think about.
It is. It's a profound question to ponder.